Hello, everyone. It's a pleasure to be here today to talk about our latest research project, VASparse, towards efficient visual hallucination mitigation via visual-aware token sparsification. This work has been a collaborative effort by our team at VASPlab, School of ECE, Peking University. Visual hallucinations in large vision language models, or LVLMs, are a significant issue that hampers their real-world usability. These models sometimes generate descriptions that don't match the visual content accurately. Our goal is to address this challenge efficiently without sacrificing speed. Let's dive into the details of how we achieve this. Before we dive into our solution, let's talk about the current state of affairs. Current methods to reduce visual hallucinations face several significant limitations. First, many of them rely heavily on additional datasets, complex training processes, or post-processing steps. This can be cumbersome and impractical for real-world applications. Second, some methods require external tools for visual localization, which is time-consuming and often not feasible in dynamic environments. Third, techniques like multi-round decoding and repeated rollbacks significantly slow down the inference speed. This is a major drawback, especially when we need fast and reliable responses from these models. In summary, these limitations highlight the need for a more efficient and practical solution, one that can mitigate hallucinations without compromising speed. So, what's our proposed solution? We introduce VASparse, an innovative method designed to address these challenges. VASparse incorporates three key strategies. First, we frame token sparsification and visual awareness as a unified optimization problem. This allows us to balance efficiency and trustworthiness in a principled way. Second, we introduce a novel sparse-based visual contrastive decoding strategy. This method helps reduce hallucinatory tokens by recalibrating the distribution of outputs. Third, we penalize syncing attention, where models overfocus on low semantic tokens, using cumulative attention scores. This prevents the model from neglecting important visual information. As you can see from this graph, our approach significantly reduces hallucinations while maintaining a high decoding speed. Compared to other methods like Chair and Opera, VASparse stands out as a more efficient and effective solution. Let's summarize our contributions. First, we're the first to explore visual hallucination mitigation through token sparsification during decoding. This is a novel perspective that hasn't been fully exploited before. Second, we propose a visual-aware token selection strategy and a contrastive decoding method that avoids multi-round decoding. This is crucial for maintaining high efficiency. Third, our comprehensive experiments show that VASparse outperforms existing methods in both accuracy and speed. In short, we offer a plug-and-play solution that is both efficient and effective, making it highly practical for real-world applications. Our work starts with a key observation: LVLM attention is highly sparse. This heat map illustrates that most layers of the model activate only a small fraction of tokens. In fact, the top 1% of tokens account for over 98% of the total attention scores. This sparsity suggests that we can prune less important tokens to speed up decoding. However, we must do it carefully to avoid losing crucial visual information. This insight forms the foundation of our token sparsification strategy. However, naive sparsification methods can actually backfire. When we tested vision-agnostic methods like TopK or FAST, we found that hallucinations increased as sparsity grew. Why does this happen? These methods prune low-attention tokens indiscriminately, often cutting crucial visual tokens. The graph here shows how chair scores worsen with higher sparsity. This clearly indicates that we need a more sophisticated, visual-aware approach to token sparsification. Digging deeper, we found that LVLMs tend to prioritize text tokens over visual ones. This density plot shows that text tokens dominate high-attention regions, while visual tokens are often ignored. This bias explains why vision-agnostic sparsification fails. It prunes the already neglected visual tokens, worsening hallucinations. Our solution must rebalance this attention to ensure that visual information is not overlooked. So, how does VASparse work? Our framework combines three core components. First, visual-aware token selection helps prune tokens while preserving visual context. This ensures that we don't lose important visual information during decoding. Second, sparse-based contrastive decoding recalibrates hallucinated outputs by comparing logits from visual-aware and masked visual tokens. This sharpens the model's focus on visual cues, without the need for costly secondary decoding. Third, we introduce a syncing attention penalty to reduce overfocus on text tokens. This helps the model maintain a balanced attention distribution. Overall, our framework is highly efficient and does not require secondary decoding or external tools. We formalize our approach as an optimization problem with two main goals. First, Token sparsification aims to minimize the number of retained tokens while preserving attention scores. This helps us achieve efficient decoding. Second, vision-aware decoding ensures that we protect important visual tokens using visual saliency scores. This prevents the model from neglecting crucial visual information. The equation here unifies these goals. The MASCIM selects tokens, and P ensures that visual tokens are not pruned recklessly. This formulation allows us to balance efficiency and trustworthiness in a principled manner. How do we select tokens? Each token gets an aggregated score combining its attention value and visual saliency. The visual saliency score P is derived from the historical attention to image tokens. No extra computation needed. By ranking tokens this way, we retain visually critical tokens automatically, even if their attention scores are low. This ensures that our model remains aware of important visual information during decoding. Next, contrastive decoding compares logits from visual-aware and masked visual tokens. This sharpens the model's focus on visual cues, without the need for costly secondary decoding. We also penalize syncing attention, where the model overfocuses on low semantic tokens like punctuation. The softmax weights here reduce bias toward these tokens, further curbing hallucinations. This helps the model maintain a balanced attention distribution. Now, let's look at our results. On the chair benchmark, VASparse achieves the lowest hallucination rates across Lava, Minic 4, and Plugal 2. Crucially, we maintain competitive speed, up to 12.9 times faster than HALC. Even token sparsity methods like fast lag behind in accuracy. This shows that our approach not only reduces hallucinations, but also maintains high efficiency. On the POPE benchmark, we outperform all baselines in F1 score under random, popular, and adversarial settings. For example, we achieve an F1 score of 62.13 on Lava 1.5, surpassing HALC by 1.6 points. This consistency across benchmarks proves that our method is highly generalizable and effective in different scenarios. The ME benchmark evaluates fine-grained hallucinations. VASparse excels in object level, existence, count, and attribute level, position, color, tasks. For instance, we score 180 on Lava's object existence task, a 5-point jump over VCD. This shows that our method can handle nuanced visual details effectively. To validate the importance of each component, we conducted ablation studies. Removing the visual-aware selection strategy spikes chair scores, showing its crucial role in reducing hallucinations. Without contrastive decoding, performance drops sharply, highlighting its importance in recalibrating outputs. The takeaway: all three components are essential for optimal results. Our framework is highly integrated, and each part plays a vital role in achieving our goals. Finally, let's talk about efficiency. By stopping at layer 0 for contrastive logits, we avoid full-ray decoding. This balances speed and performance, achieving 27.7 tokens per second with minimal hallucination. Compare this to HALC's 2.15 TPS, and the advantage of our approach is clear. We achieve high efficiency without compromising accuracy. To summarize, VASparse mitigates hallucinations by leveraging sparse attention with visual-aware pruning, contrasting logits efficiently, and penalizing attention sinks. It's a plug-and-play, training-free solution that is faster than state-of-the-art methods. We've open-sourced the code, so feel free to try it out and see the benefits for yourself. Thank you for your attention, and I'd be happy to answer any questions you might have.